Okay. Good morning, everyone. Most of you knows me. I'm Mujtaba, and in this meeting, I'm trying to explain some fundamental, backgrounds for lattice-based cryptography, and then we will go through the Kyber crypto system to see what's going on the finalists in the NIST competition. So feel free to interrupt me and ask your question during this presentation because it takes actually a long time, and you maybe actually forget your question. So interrupt me and ask your question to have more interactive meeting. So in this presentation, we will have some brief introduction about the lattice-based, and then we'll go introduction about the cryptography, and then we'll go through the lattices and lattice-based cryptography. Then we will see some Sage code example for lattice-based crypto and also Kyber, and then we will go through the Kyber specification and architecture. So as you know that the first PQC algorithms have been actually standardized recently, and Kyber has been selected after almost 7-8 years of the PQC competition. Crystal's Kyber has been selected as a finalist and the first post-quantum crypto algorithm in actually key exchange mechanism in the left side here. While for the digital signature algorithm, we have 3 finalists and chosen algorithm. Between them, as you see, the crystals dilithium are very close to the Kyber. So if we understand the Kyber, it would be very easy to handle and understand the algorithm in the dilithium. And they have they share the same platform and arithmetic. So it would be good to have a combined algorithm to combine architecture specifically for the hardware to somehow support both these algorithms. So the lattice-based crypto has different applications. For example, we can use it in the key exchange mechanism, similar to the Crystal's Kyber. Also for the digital signature algorithms, for the PQC, for the quantum safe as a quantum safe solution in the signatures, such as the crystals dilithium. It can be also used for the hash function, and one of the most important applications of the lattices are fully homomorphic encryption, which are widely used in current in academia and industry applications. In the fully homomorphic encryption, you try to encrypt your data and send it through the when you want to use a cloud-based applications, instead of sending your data there and the data does not need to be decrypted over the cloud, over the service, and the service will be applied over the encrypted data, and the results will be converted, will be sent back to you, and then you can decrypt the data at the very end of the this chain. So no one from the cloud service provider or cloud infrastructure provider has access to your data. All of them are working on the encrypted data, and your data would be safe. Therefore, for most of the important applications, for example, for medical information or other information that, or some money-based applications, instead of sending the data and the in current applications, your data will be encrypted here, will be sent to the cloud, and in the cloud, the data should be decrypted, and the applications, the service should be applied over the decrypted data, the pure data, and again for the communication, data will be encrypted and decrypted. But we removed all these actually decryption and encryption procedure in the cloud, and all of the service providers will use the encrypted data. Therefore, your data would be safe. Okay, so what is the lattice? A lattice is actually can be defined as a combination of the some vectors. Suppose that, as an example, you choose two vectors of B1 and B2, and then the lattice can be defined as a Z1 B1 plus Z2 B2. Therefore, if you choose different Z values for Z1 and Z2, you can find different points over this specific lattice. Any questions so far? Okay. So in this example, suppose that we have these L1 and L2 here, and we choose different Z value for Z1 and Z2. Therefore, we have different points, and these green points, as you see in this figure, describes our lattice L. So what is the hard problem in this concept? One of the hard problem here is CVP. Suppose that you have a lattice, and then I give you a point, and I will ask you find a point over the lattice which is closest point to the given point. When the suppose this is actually our given lattices, including the B1 and B2, and as you see here, let me. Okay, so when the angle between the L1 and L2 as a basis for our lattice are almost 90 degrees, the finding the closest point would be very easy. So it's not a hard problem. For example, in this case, when the B1 and B2 is similar to the given vectors here, as you see here, and the angle between them is almost 90 degrees, you will see that by these equations, suppose that I ask you to find the closest point over the lattice, the given lattices, what is actually the nearest point to this point. So you try to solve this equation and then find the Z1 and Z2. This is two actually unknown variable here, and you have two equations, so you can easily find the Z1 and Z2. And since the Z1 and Z2 should be integer values, you have to estimate the Z1 and Z2 to this value, and then when you find, you can easily find the nearest point here by actually the computed value for Z1 and Z2, and it gives you this point over the lattice 30 and 6, and this point is nearest point to the given point. So until now, there is no hard actual problem. But if I give you a new lattice, while the vectors are almost actually parallel, finding the nearest point is a hard problem. So the angle between the Z1 and Z2, sorry, the B1 and B2, while the B1 is this vector and B2 is this vector, the angle between them is almost actually 0. And then if I give you again the previous point, 27 and 8, and I ask you for finding the Z1 and Z2, you will find these two values, and then by changing them to the integer value, you will reach to this point over the lattice, while this point is not the nearest point to the given point. So this is actually the base problem in the for using the lattices in the cryptography, and actually making a hard problem. Any questions so far?
Hey, Moshtaba. This is Daniel. Good morning, man. I have a quick question.
Yeah.
So what I guess what modifies how hard this problem is? Is it the size of the lattice?
Yeah, it depends on the size of the lattice. It depends on the in the cryptography, we also we use the finite field again. We choose a ring, and all of our computation should be modular. So the chosen prime number, the size of the B, the number of vectors here, all of them actually would affect on the hardness of the problem.
Gotcha. Okay, thank you.
No problem. Any question? Okay. So the difficulty of the lattice-based crypto or lattices are based on the shape of the bases in the lattice, and if they are very close, as almost actually parallel, as we see, it would be actually a bad set of the B, and therefore we will have a hard problem. So in this actually figure, you see a good basis, so it's would be an easy problem, while for exactly the same points as you see here, we can define different B's, and it gives us a bad basis, and it would be a hard problem. Okay, so let's jump to more actually closest.
I have a question.
Yes.
So is there a range? So when you're saying it's a difficult problem or good or easy to solve, are you saying that the problem you're encountering will be difficult, or is it the actual structure of what you're looking at? Like if you're working on something and you notice that it's not at 90 degrees, you have to try to make your problem fit in the 90-degree area so that it's computable. I'm kind of confused on that.
Yeah. So when you are defining your problem at very first step of the designing your crypto system, you have to put some rules, such as the number of, for example, B, how you choose actually the B, because you are trying to, for example, choose randomize actually values for each coefficients of the B. So by choosing the specific rules for generating the value of the B and the number of the actually B as a basis of your lattice, you can somehow define the difficulty of your problem. So for example, in this slide that I'm showing you, you will see that how we can add some more features to the lattices to make it more difficult. So by adding some different features together, you can define a crypto safe, quantum safe actually problem. By the way, the difficulty of each lattice problem is can be actually computed by some math actually fundamentals. I'm not expert on it, but I know that they define this is, for example, the NP-hard problem with this feature, but this problem is more difficult than the previous problem. And if you review some actually papers, most of them were, for example, 15 years ago, when the lattice are coming to were coming to actually crypto. You see that how they choose and change different features for defining the lattices and make it more difficult for the cryptography system.
That's cool. Thank you. So you're saying that, so in your one picture you had, you said that most of the points had a 90-degree angle. So for you to make your crypto system more difficult, you would maybe make them kind of randomized. You don't want them to have, okay.
Yeah.
Great, thank you.
You are very welcome. Any question for our audience? Okay. So until now, we realize how we can define the lattice and how we can define a hard problem. And now we are trying to add more features to lattices. One of them, which is more actually applicable and it's used in most of our current crypto system, are learning with errors, or LWE. In this method, you choose a uniform matrix A, and then you choose a vector of the noise defined by S. So the S here is your secret key, and the A here is A and T together are your public key. So if you have A and T, as you see here, it would be very easy to find the S, because you can compute the inverse of the A, and A inverse times T results in the value of the S. But if I add a noise with very small coefficient to the product of the A times S, it would be again a hard problem. Therefore, in this actually equation, if you have these blue values, you cannot find the value of the secret key, which is defined by vector S here. For example, you see here we have some values for the matrix A, and then we have some secret value defined here, and then we are calculating the value of the T. So again, by if the value of the A and T are given, you can compute the inverse of the A, and then the product between the inverse of the A and T results in the vector of the S. But in the right side, we are changing the value of the T by adding some small noise to the product of A times S. So having the value of the T and A, it would be a hard problem to find the value of the S. So based on this concept, which is defined by, which is called learning with errors, we can define two different hard problems. One of them is finding S. So you have the A and T, so they ask you to find the value of S. It is a hard problem. And another one is decision version, while you have to distinguish between the LW samples from a uniform randoms vector. So we are using the LWE in most of the crypto system. So any question so far?
Is
I have a
the
quick question.
learning? Oh, sorry.
No,
go ahead.
no, go ahead, Emma. No, go ahead.
Oh, okay, thank you. Is learning with errors like I combined with machine learning? Because that kind of reminds me of like machine learning. Or is it?
Yeah, maybe most of them are based on some math concepts. So I guess you will have some similar concept in machine learning or other actually field as well.
Okay, thank you.
Yeah.
Quick question, Mushtaba. So you
Yes.
just have given like a noise distribution, but that distribution is not uniform, right? It's, at least that's my understanding, like for how you sample the noise.
The noise actually, the noise distribution should be given in the, for example, for different crypto systems, such as the Kyber, Saber, they have different noise distribution. And each distribution has some specific factors. For example, the center of the distribution, I forgot the name, the theta or something like this for the distribution, but is defined based on your crypto system, based on your problem.
Okay, gotcha. So different lattice-based systems will require a different distribution.
Yeah.
Okay,
They
very interesting.
somehow defining actually their specification.
Gotcha.
But for the
okay,
A,
thanks.
yeah, but for the A is actually uniform.
Yeah, I got that. Okay, thanks so much, Mushtaba.
No problem. Any question? Okay, so suppose that you are working with a large values, large actually size of the A, and when we know that if you have a matrices of A with n by m, and then you have a error of the E here, finding the value of the E if let's assume that the coefficients of the E are binary, so you can choose the value of the 0 and 1 for each of them. Therefore, since the E has m coefficients, you have to choose 2 power of the m different trials to find the value of the T. So it is a hard problem when the m is actually a large number, and best algorithms to solve this problem takes 2 power of O(n). So it would be a hard problem with a large value of the n and m, because you have to guess the each coefficients of the E to find the value of the T.
And what are the typical, like what's the size of the E vector typically for Kyber?
Yeah, for the Kyber is 256.
Okay, makes sense. Thanks.
Any question? Okay. So based on this concept, LWE, we are defining 3 different crypto systems. The first one is exactly similar as we see. So as we saw here, we have a matrix A, and matrix A has is actually n by n. So it has n square coefficients. Sorry, it should be n minus 1, but I forgot it. And then for the vector S, we have again n coefficients, and for the matrix, vector E, which is our noise, we have again n coefficients, and then we calculate the t. So for this method, which is the pure LWE, you see that for storing the matrix A, you have to store n square coefficients. So the required storage is n square. And also for computing the product of the A and T, A and S, you have to compute n square different multiplication. For example, A0, S0, A1, A01 with S1, A02 with S2 until the end. And for the this is the NS multiplication. For the second row, again, you have n multiplication. Since you have n rows, the total required computation here is in order of the n square. So when the n is a large number, such as the 256, the value of the required storage and the required computation, actually power, are too much, specifically for some low resources platforms such as the IoT devices. So there are some actually methods such as the ring LWE that reduce the required storage and computation. For RLWE or ring LWE, we have to choose our first column as you can see here. And then for the second column, we are shifting our first column by 1 downward. And then the last coefficient would be placed as in with a minus actually sign as a first coefficient here. So you can, if you have the first coefficient, first column here, you can regenerate all the columns for the matrix A. Therefore, the required storage for this method is decreasing to only n coefficient, as you can see here. And also, since these vectors, these columns are not independent, there are some methods to reduce the complexity of the multiplication between the matrix A and S. These methods are very similar to FFT in signal processing, if you are familiar with. So we can reduce the complexity of computation here to n log n. This method in lattices called NTT. So we can reduce the storage and computation. And there are another method, which is modular learning with errors, which is very similar to RLWE, while we choose different matrix A. So for each matrix, we have the same structure here. Therefore, suppose that for K equal to the 2, we have 4 matrix A, and we have to store the first column of each vectors. Therefore, the required storage for this method is K square n, K square because of the number of the matrix A, different matrix A, and n for each for first column of each of them. And the computation complexity between them is also K square n log n. This method is used in the Kyber. Any questions so far?
Quick question, Mustafa. So if MLWE is a little bit slower and requires a little more storage than ring LWE, why does Kyber use module?
Yeah, it's actually based on the LWE, but we can define the, we can have the different security level by choosing different value for the K. So if it gives you more actual flexibility. In the Kyber, with different value of the K, you can reach different security level. In the NIST, there is a requirement to provide the crypto system for NIST security level 1, 3, and 5. And in the Kyber, by choosing the K equal to the 2, 3, and 4, it provides 3 different crypto systems to cover those 3 security levels. But here, in this method, you have to increase the length of the size of the matrix A.
Right.
But here, everything is the same, and you can easily change the value of the K by adding more matrix A to increase the required security.
Gotcha. Okay. So even though it looks like one is slower than the other for any given security level, the module is faster than the ring.
Regarding which one is faster, I guess for the same security level, it would be the same, because suppose that the K is equal to the 1. So you reach to the first actually method by K equal to the 2. You have to increase it maybe 4 times, and it gives you n will with 4n, it would be 2 power of the, I guess both of them are the same, but it gives you more flexibility because the matrix A is the same, and you can repeat it several times with the same code, with the same architecture, specifically for the hardware, with the same definition. For example, the matrix A are defined the same, and you only have to repeat the procedure several times to have to provide different security levels. But the split between them is the same, because the module learning with errors is exactly similar and equivalent with ring learning with errors.
Okay, thank you very much.
No problem. Any question from others? Okay. So we are actually speaking about the lattices, and it's split to 2 different categories, mainly. One of them is LWE that we discussed, and one of them is LWR. In the LWR, instead of adding the noise, we try to somehow cut, for example, we are trying to round the values, and it gives us somehow the randomization instead of adding the noise. So this is another actually method that can be used for adding the noise to the product of the A times S. And LWE also is categorized to 2 different methods, as we saw. Ring LWE, which was used in the New Hope. New Hope was in the round 2 of the NIST competition, and modulo LWE is defined in Kyber. One thing that I remember for the New Hope, it couldn't provide the security level 3. It only provides the security level of 1 and 5. So as I mentioned, using the modulo LWE, and by choosing different value for the K, it gives you more flexibility to provide different security levels. So Kyber can provide security level for all those 3 requirements. And also for the LWR, it categorized in 2 similar actually groups, ring LWR and mod LWR. Ring LWR was used in round 5. It was again a crypto system defined in the NIST round 2, and the Saber was in the NIST round 3 as well as a finalist, but Kyber has been selected. Any question?
Very much so. I have another question, man.
Yeah, sure.
So at the bottom LWR, you say the noise comes from rounding to a smaller interval. What exactly does that mean?
Suppose that you have a circle, and then you divide it to 4 different regions. Okay, suppose that you have your prime value is 13. Okay, so your value should be from 0 to 12. Okay, if you divide these range to 4 different regions, you will have, for example, 0, 1, 2 in the first region, 2, 3, 4, 5 in the second, and so on. Okay, so you round each values. If you have 0, 1, 2, you will round it to the 0. If you have 3, 4, 5, you round it to the 3. If you have a 6, 5, 7, you round it to the 6. Does it make sense?
Yes, it does. Thank you.
Okay. Any question? Okay. So let's see how the LWE can be used for encryption. First of all, you have to create a paired key, secret key, and public key for the Alice through the keygen function. In this operation, as we saw, we have to compute the A times S plus E, which is equal to T. So, sorry, we are suppose that the coefficient in matrix S and E are very small, and matrix A is also a random value. We call matrix the concatenation of the matrix A and T as a public key of the Alice, and S as a secret key. So using this computation, you can define the secret key and public key, and then you will have a paired key for Alice's. So after that, the public key of Alice will be sent to Bob, and Bob chooses his own random value as a vector of the R for encryption of the message M. So here we are trying to encrypt the message M and send it to the Alice to provide the message M will be used to provide a shared secret key. So Bob will use the public key of Alice, AT, and then by calculating R times AT and adding 2 noise of E1 and E2, and again by adding the message M, he can provide the cybertext of U and V. Okay, and U and V will be sent to the Alice to recompute and regenerate the message M. Let's see how V can be calculated. So if we come back again here, V is the product of R times R plus E2 plus M. So I showed here R times T plus E2 plus M. And the value of T is equal to A times S plus E. So the calculation between them is R times A times S plus R times E which is, since the E has a small coefficient, we are showing it as a noise here, plus again another noise here, plus message M. Okay, so, and if we also see how the U is calculated, U is equal to R times A plus E. If I come back here, you see that U is equal to R times A plus E1. So, sorry, U is R times A plus E1. And if we compute the product of U by S, you will see that it's equal to R times A plus C. This is the first term. And for second term, we have a small noise plus S, which is equal to the small noise shown by this red value here. So you see that this value, R times A plus S, is also in the V value, and therefore the U times S is almost equal to V minus M. The difference between them depends on the value, the size of the noise here, and in the here in the V equation. So Alice used this equation to compute the V minus U and S in decryption operation to calculate M plus a noise. And therefore, he can decrypt the message M by reducing the message, reducing the noise here by some method. And therefore, by having the secret key, she can regenerate the message M in decryption operation. Any question?
So is R the same value as S?
No, R is actually the Bob random value, and no one knows about it, because if you know the value of the R, you can calculate the message M. But no one knows about the value of the R.
So is S, well, I guess I'm asking because they're both the same color, so I thought that maybe it has to do with the structure of the equation, where it's a similar equation from Alice, but with Bob.
The same color here means both of them are somehow secret and no one knows about it. The yellow here means noise, and the blue here means it's public.
Oh, okay. All right.
Yeah.
Thank you. I was a little confused. Thank you.
No problem. So using this method, you can easily regenerate the message M, and therefore this method LWE can be used for creating generating a shared secret key between the Alice and Bob. So if we assume the message, the matrix A has the size of the message A is n by n, you will see that for each bit of the message M, you have to send a lot of the data between the large size of the data should be transferred between the Alice and Bob. So you see that the size of the public key here is n by n plus n by k, and the size of the cybertext here is k times n plus k. So it's actually a large size of the data between these two parties of this communication, and therefore one of the actually disadvantage of the lattice-based crypto is the large of the public key, the large of the ciphertext, and actually the size of the key. If you are familiar with the ECC or psych in the PQC algorithm, you can see that the size of their keys are small. It means they need only, for example, 300, 200 bits. But here we are talking about in order of the thousands, actually, bytes. So it's too large. Any question?
Yeah, Mojtaba, I have a very cool question. In the decryption step, the result is m plus the error. Is that affecting actually the message value, or?
We can somehow reduce the message, because I will show you how we can reduce the message in the Sage code. But there is a method that we can regenerate the exact message M in the decryption method.
Okay, thank you.
You are very welcome. So here we are. This is actually a very simple Sage code for this LWE method. The value of the N is equal to, for example, 4, the K is 1, and the Q is our prime value here, because all of our computation should be, again, modular. The Q is equal to the 13. So if I choose a random value for the A, similar this matrix, and I choose the value of the S again in random with a small coefficient between -1, 0, and 1. So this is my S value, and this is my, again, noise vector with a small coefficient between -1, 0, and 1. The value of the A is between the 0 to Q minus 1. It's actually in our field. The modular multiplication between A and S is equal to this vector shown here, and then, sorry, in the Bob side, we choose again the random value of R with a small coefficient, 2 vectors of the error with a small coefficient, and the message M between 0 and 1. So you will have the message M here, for example, equal to the 0. Then you will, in the encryption method, you have to calculate R times A, and the results would be actually should be added with noise of E1, and it would be our first ciphertext equal to the U, and for the vector of the V as a second part of the ciphertext, we will have to compute R times T plus a noise of the E2 and the message of the M. So the method that is chosen in crypto is, if the message is equal to the 0, we have for each bit of the message, each bit of the message is equal to the 0 or 1. For 0, we are choosing the Q divided by 4. For the 1, we are choosing 3 by 4 times Q. So for RQ, which is equal to 13, if the message is equal to the 0, we are choosing Q by 4 is 3. And if the message is 1, we are choosing 3, 9. Is it clear how we choose the queue, the message?
I have a little question again. Is that producing, like, somehow making side channel attacks applicable over here? Because
No, it's not related to side channel. I'm
when you
suppose that this is our field, which has 1, 2. Sorry for my bad handwriting. And this is our Q here, very end, Q minus 1. Okay, which is equal to 12 in our case. Okay. So is it clear what is it? Is our field between 0, 1, 2, 3, 4, 5, 6 until Q minus 1. If the message is 0, we choose this value. In our case is 3. If the message is equal to the 1, we choose this value in two sides of the our ring, which is in case is equal to the 9.
So Mojtaba, how does this process differ if your message is greater than 1 bit?
For each bit of the message.
Oh, for each. Okay, got you. Okay, so if your message is 1100, then you choose 3399 or 9933. Okay,
Yeah,
got
yeah.
you. Okay.
And then for each, because the figure that I showed you is related for each bit of the message. So if the vector of the, if I came back to, how can I stop? Okay. If I came back here, if the size of the K is increasing, you will have different bit of the message and different bits of the E and different results for the R times T. So for each bit of the message, we have to choose a value between the 0 and 1. And if we choose 0, we have to choose 3. If we choose 1, we have to choose 9. Okay. So since these two values are too far from each other in two sides of the equation, two sides of the field, if our final results here, okay, if it, how can I change the color? It's too hard. Okay. So if I divide this field to two sections, if the addition between the message and M is something between 0 to Q, half of the Q, it means that we have to choose message 3. If it's in the other side, we find that the message is equal to the 9. Is it clear?
Yes, thank you, Mojtaba.
No problem. Mila, does it actually make sense? It's actually exactly how we can reduce the message here.
I understand, but actually, I'm not sure, because we choose for each bit of the message plus the error, we choose respectively 3 or 9. But then, so let's say the bit of the message M0 plus the bit of the error E0. So if it is bitwise, isn't it returning 0 or 1 independently? Like,
each coefficients here in the E2, in the T, in the A are in the field of the Q are not actually 0 and 1. Okay.
Okay, we can do that. Okay, now I understand.
So
It was bitwise, sorry.
yeah, it's actually for the message, we choose for each bit of the message. If it's actually 1, we choose 3 by 4 times Q. Oh, it's very hard to me to write here. And in the if it's actually 0, we choose Q divided by 4. And based on that, we have to compute this computation and find the value of the V. It's not actually the bitwise. It's actually all of them is modular respect to the value of the prime, the Q. But at the very end, in the decryption, for each bit of the message, for recovering each bit of the message, we have to figure out if the results between the M and noise is in the right side, because we know that the value of the noise is noise has actually a small coefficient. So the value of the message, if it's 3, the noise can change it until here or here, not more.
Okay.
It's actually defined based on our specification, how we choose the value of the E as a noise. And if the message is equal to the 9, it can change it until to Q minus 1 and here until here. So we are trying somehow around the results to give the exact value of the message.
Okay, thank you so much.
No problem. Any question? Okay. How we can clear the station here? Okay, I guess. Perfect. So in the decryption, Alice compute the cybertext times secret key, her own secret key, and the results should be subtracted from the V as a second part of the cybertext. So you will see that the message here, the message plus noise here is 2, okay? So here at the very last step, we define if the message is bigger than Q divided by 4 or less than 3 by 4 times Q, it means that the message value is 1, otherwise is 0. And then we compare it with our actual message, and we can see that we can regenerate the message correctly. So our actual message here was 0, you can see. But after this computation, by adding the noise, we recovered the message plus noise is equal to the 2. And then by using this technique, we can reduce the noise and find that our actual message is equal to the 0. Any question? Okay. So for the Kyber, we will see that we have 3 different security levels. The value of the N for all of them is the same, 256. The Q here is 3329. And the value of the K here, the size of the number of the matrix A is increasing to provide higher security. So the size of the secret key, public key, and ciphertext also are shown here. And as I mentioned before, you will see that their size are too large compared to classical crypto system, such as the ECC.
Moshtaba, before going here to architecture, can you here give an example of, so remember we had A, B, E. Can you give an example of A and B with a polynomial of degree n and mod q? So give a small example. I would like them to see, for example, A could be anything. So like write a polynomial and they see that we do, and also mod operation.
Yeah, sure.
Modular operation.
Yeah.
You know what I mean, right?
Yeah, yeah. Let me share my Sage code here.
So you can.
I guess in the Sage, I can actually print it very easily and then.
Yeah, go to Sage. Yes, very
Yeah.
good, probably. So it's, for example, you had there actually Q7 and N4, I think you had on the example.
Yeah, it can be defined. So
Yeah, there you go.
here, if I change the value of the n in the Kyber size is equal to n.
No. I mean, first write the
matrix A.
polynomial for A. I want them to see before going to bigger
it's
number.
actually, of
what
course.
Does it? What n means? Write a polynomial for A because you choose A, something like coefficient less than 7, and I think degree less than n, right?
Yeah, I'm trying to show the value of the A here.
This is
how
big.
we can actually find the value of the A. Suppose that in our example,
7.
while
4,
n
yes.
was 4 and q was 13, we have the matrix A equal to this. Okay, this is the matrix. The matrix is each column of the matrix here is actually a polynomial. So let's say only one polynomial to have a better understanding.
Yeah. Yeah, if you can show it, or Poly, good. Size.
Okay, so suppose that the size of the degree of the polynomial is 4, and our prime field is 13, which is equal to the q. So each polynomial here is defined as a vector of 4 coefficients, and each coefficient is between 0 to q minus 1. So it's 5, 8, 8, 7 in this example, or we can have different polynomials.
How do you write it in math? That's what I'm saying. How do you write this polynomial? You say A equal to 7x to the power something.
No,
like that,
it's actually only a vector with different. If I want to make it in
I know for
7x,
yes, 7x to the power
3 plus 3 times x by 2 plus 3x by 1 plus 8.
Yeah.
So it means that we have a poly here. Yeah.
Exactly.
So each coefficients here are equivalent to each coefficients of this polynomial.
Exactly.
Yeah.
Yes.
Yeah.
So same thing applies to B. So when you write this A and B, and then we do everything on these polynomials, right?
Yes.
We can multiply these polynomials mod Q and N. What is the reducible polynomial for xn plus 1, right? X to the power n plus 1. Where is that?
X power of?
X to the power n plus 1. Is this irreducible polynomial mod that we do?
No, we are actually, it's not actually modular. we cannot actually somehow reduce the polynomial. But how we can do here? Let me think about it.
Coefficients are
reduce?
mod q, right?
Yeah,
If you-
coefficients are mod q.
Okay, how about the polynomial?
You are saying that what's happened with
That's what
degree
you was
more than the
thinking.
more than the n.
More than n, you reduce x to the power n plus 1.
Yes, yeah.
There you
It's
go.
actually somehow there is defined by based on our ring. So after that, it should be reduced. But I forgot actually their equation here, how we can reduce it.
Reduce x to the power n plus 1, right? Is that same as all lattices? I think
I don't know. I'm not sure about it. I have to check it.
okay. But
And I got actually your point, but I'm not sure about it, how we can reduce
okay.
it.
So simply, if this is, for example, poly A, or A is that you wrote 7x cubed 3x squared plus 3x plus 8. So what would be B? You write another B, for example. Yes, write poly B. So another one. Yeah. You can generate array of another random up there, poly B.
Okay.
You know how to do that? B. Yeah. Okay. Now there you go. But this is so what is our okay? N is 4, and those are, and Q is 13. Good. Can you make Q a little bit smaller so we can easily do mod 13 is hard for me.
5 is good.
5 or 7. Make 7 easier. There you go. So now you see we have two polynomial. Why did you change? Okay, yes. Thank you. 3, put 0, that's fine. Yes, I just want to see them. And then 4. Okay, these are two polynomials, right? We can add these two polynomials. A plus B will be 6 plus 9, 15, x cubed. The other one is, sorry, what's the other one? 0, 0, 2, 4. Good. So A plus B will be only 6x cubed, no x squared, 8x plus 7, right? So since it's mod 7, coefficient can be reduced. Mod 7. So that the resulting, if you want to write here what your hand, I think I just want to show them A plus B.
A plus B for the 7 for the, here 12.
No, just write A plus B equal, or poly A plus poly
plus B for the for the
yeah. I just want to 6x cube
x cube plus 0x square plus 8, which is reduced to the 1.
No, write it and then yes. So 8x plus 7. Okay.
Yeah.
Now we have, these are actually reduced mod Q, right? Coefficient. So 6 is less than 7. Good. The other one is 0. 8 should be reduced. Now reduce it. So go ahead. 1. Not factorial 1. Yeah. And then 0. Good. So this is how we do arithmetic over polynomials mod this. So how about, and also, since we are adding two polynomials, the degree of polynomials are not changing, right? You see that we have x cubed biggest. So if it's less than 4, we don't reduce. If it's more, we have to reduce it. For example, when you multiply, right? If you multiply two polynomials, what's going to happen? A times B then is big, I think. So students, you can play with it if you'd like. So you multiply these two, you got to multiply all coefficients. If you write it in short format, that's easier. You want to do that? 6, 0.
For example, for some actually coefficients to see how it's.
Yeah. So the power, so now you see that x5 is more than n. You see that n is 4 and we have to reduce it. So yes, Well, actually, that's 0. Go
Mhm.
to the next. So 6x
It's
cubed, 6x4, 6x4.
6
Sorry,
2
12x4.
12
12x4.
plus, yeah, and nothing else because all of them are 0.
Okay, 12x4.
X4.
So this is gonna be,
It should
okay.
be reduced by Q, which results in a 5.
No. But how about take your mouse a little bit up? I
Oh,
don't.
it should
Okay.
be,
Yeah. So 12 will be reduced mod 7. X4 will be reduced by n, which is x to the power plus 1. X to the power n plus 1 is your irreducible polynomial. So what you do basically, you say, so you know, I did in the class, probably everybody have taken my class. So yes, but what do you put for x?
but
X4.
here,
You
mhm.
say x4 will be -1, right?
Yeah, you're correct.
Substitution. So they will be, okay, now multiply by -1. And then it is going to be -5. And -5 mod q will be 2. That's it.
Mm.
You'll write 2 there only. So that's how we multiply and reduce operations. And that's it. Plus, and then you keep going.
Yeah.
So I think when I was teaching binary binary arithmetic over polynomials, I taught this in the class.
Yes,
So,
exactly.
but this is how it works basically. How we do addition, multiplication, and reduction. You do 2 reductions. One is mod q for coefficient, and the other one, degree of the polynomial should be reduced to the size of n. They should be less than n. If not, you have to do reduction, x to the power n plus 1. So by hand, we say x to the power n is -1, and then you substitute, you get the things, the numbers, and the rest are basically what you're explaining, which is good.
Yeah. Sorry, I forgot actually how we reduce the X4 here.
Yeah, that's for, well, you don't write it in codes basically, right? But this is even for teaching only, to understanding how you substitute and reduce multiplication of 2 polynomials. Anyway, thank you, Mustafa.
No problem. Any question, students? It's actually important what is actually polynomial means here, and how we can do arithmetic, modular arithmetic over them. How we can add 2 polynomials, how we can multiple 2 different polynomials over our ring modulo Q. So the degree of the polynomial is defined by the value of the n, and all arithmetic should be modular for the coefficients respect to the q, and for the x respect to the degree of the polynomial. Any question? Okay. Can we go? Can you see my slides?
Oh, this is Python. This is your Jupyter.
Oh,
Team, if you have any questions, please ask now. I mean, that's thing that you gotta ask. It's gotta be clear for you. So
yeah,
questions.
Don't hesitate to ask, because it's not actually an easy problem.
I was actually wondering if you were going to have another SCAL workshop.
Sorry, pardon me? Oh.
If you were going to do another side channel analysis workshop.
Okay, but
with so like as a continuation of what you were doing today with the lattice, and showing us how you've used the tools for the lattice-based cryptographic system.
before actually going through the side channel of lattices, we are trying to understand what's going on in the lattices and how we can create and generate actually a paired keys, including our secret key and public key, and the math behind it. So first of all, try, because when you're trying to secure your crypto system, you have to know what's going on exactly there and what is actually the source of the leakage. So before actually going to another SCA workshop, we have to understand the lattices and the arithmetic here. So is there any question, problem, issue with all this math here? Please ask now, and I will try actually to explain it better.
Are you sharing your screen? Because it says that I can't see. It says like you're loading.
Can you see?
I'm not sure. It
Yeah,
says
you're-
like,
We see the screen. We see Kyber parameters.
Yeah.
oh, for me it's just loading.
Refresh it. Yeah, we'll have probably later talk about the side channel stuff as well. But today we want to, you guys to be familiar with these. What this parameter Kyber 512 means that n degree of polynomial that we are reducing is x to the power 256 plus 1. Q is your prime. This Q is a prime number, right? 3,329 is a prime number. And you do mod of those coefficient of this Q. And that n is the largest degree that your polynomial can have. Otherwise, you got to reduce it. And then on the other side, what is K actually? K234?
K is actually the number, how we can create the public key. So it's this is the number of the matrix with the polynomial of the n.
Yeah. Okay, which stands for, gives us the level of security.
Security.
So,
Yeah.
and then on the right side, we have a size of the, in bytes, the secret key,
Public key.
public key and ciphertext.
Yes.
So
For example, in the NIST security level 1, Kyber 512, you
Mustafa,
have two
yeah.
polynomial of the degree 256.
Moshtaba, do you know how we get from these NQ to public key size of 800? Do you know that? There is some computations. Do you know how to get there?
Should be here.
Yeah.
Something similar to, for example, K times N plus K for the cybertext, and for the public key is N times N plus K.
N times N plus K.
Because the A and T are concatenated to each other. So it would be N different rows, and we have N plus K column. So
Can you multiply them for that example to show us 800 key size? Not really.
256 plus, for example, K is 2. It should be something like this, 256. It would be the number of the coefficients here in 256. Oh, it's actually LWE. In the M, LWE is decreasing. Yeah, because we have to reduce it. So if I go here, let's clear it that the number of the secret key, the public key and cybertext here is not only actually the concatenation of the cybertext, because they add some seed and other things to the end of the message and add some hashing algorithm. So it would not be easy to calculate the multiplication between them and get these results. If there is any actually equation, I'm not aware of it. But for the LWE, because the Kyber is modulo LWE, but for the LWE are exactly here, n times n plus k for the public key, and k times n plus k for the ciphertext. And for the secret key, it's n times k. For modulo LWE is different, and also for the Kyber, they add some hashing results and will concatenate it with the public key to get these results.
All right, later if you figure out, I think I checked it before, but you can check the Kyber website or something. If there is an equation or something that we can compute these, let us know. I think interested to know how we get and how you can play with these and this n. So n stays the same for all, right?
Yes, and it's the
And
same.
Q2, okay. Yeah, sounds good. So ciphertext size and yeah, symmetric key, secret key size. Guys, do you have any questions?
Will there be anything given to us so we can try to, I guess, practice something in a small scale of this, like how you were showing us in Jupyter, maybe?
Moshtaba, yes, there is something. I had a full Python for Kyber. Did I send you?
Yeah.
Okay, can you
Yes,
clean it up if you can share it with everybody so they can start playing with it?
Yeah,
Sage or Python.
I will send it to you.
Yeah, that's it. I think I send it to you, and then so if you could put instructions how they can run it, the Kyber. I think the numbers are big, but if we can make it like small for the purpose of presentation, that would be good for regenerating stuff.
Okay.
Go ahead if you want to keep.
Yeah, sure. Any questions so far about the parameters? Okay. So what's going on inside of the Kyber specifically? So in the Kyber, first of all, we have to generate the matrix A as a public key and vector S as a secret key and the vector E for our noise. We are trying to generate them using some noise generation, noise generator actually component. We are using the Ketchuk, which is the SHA-3 unit. Is actually a hashing algorithm. And also we have two sampling unit, one of them called CBD, one of them is rejection. So we feed the Ketchuk a seed, and then Ketchuk will generate us by actually running Ketchuk for several times, we can generate lots of the random values. So for the matrix A, we are using the rejection. Rejection, what does it mean? In the rejection, we choose some bits of some actually, for example, in our case, since our Q in the Kyber is 3329, 3329, we need only 12 bits, okay? The Ketchuk provides a stream of the random values, random bits. So in the rejection, we choose 12 bits. And if the 12 bits, the value of these 12 bits are less than our Q, it means that we can use it as a coefficient of the matrix A. Otherwise, we have to reject it and go to the next 12 bits. Does it make sense, everyone? Okay. For the CBD, So this is actually the rejection, and we, for example, for the Kyber in security level 1, we have to choose 256 coefficients for each vector, and our matrix A in the Kyber in this security level, we have to provide 2 polynomials of degree 256. Therefore, we have to choose 512 different coefficients and put them in 2 polynomial of degree 256 using this rejection. Does it make sense? Okay. For the CBD, CBD is actually a central polynomial distribution. We there are coefficients for the matrix A, matrix S as a secret key, and error should be between -2 to 2. And therefore, we choose 2 bits of the random value, and then create the matrix vector S and vector E as a noise using the CBD. Okay, so we have to compute A times S. Let's come back again here. We generate the matrix A using the, we choose only first vector of the matrix A, because if I come back here, you see in the modular learning with errors, you have to choose the first column. And for K2, sorry, we have to generate 4 vectors, 4 polynomials of degree 256. We choose the first column of each matrix, and then using the CBD, we create and generate the vector S and vector E. And now we are trying to compute the multiplication between A and S using entity method. So for the polynomial multiplication.
Hey, Moshtaba, hey, quick
Yes.
question. Wait, I'm a little confused because you just said you only take the first column of matrix A.
Yes.
Can you explain that again, please? I think I must have.
If you remember, I told you in the module learning with errors and ring learning with errors, we have to only choose the first column, because other columns are somehow can be extracted from the first column. For example, the second column is equal to first, shifted by 1 to the downward.
Right. But okay, but then to compute like A times S, you use the full matrix A, correct? Like, so you would compute the first column, expand it.
So if I use the full matrix A, it means that I have to compute, similar to this method, I have to compute an S square multiplication. But I told you, because of the relation between these columns to each other, there is another method similar to FFT, which in the finite field it calls entity. We can only compute the first column here, the multiplication with between the first column here and the matrix S by some other actually multiplication. So you do not need compute the multiplication between all these vectors to each with matrix S. So it reduced the multiplication from n S squared to n log n.
Okay, gotcha. Thanks.
No problem. So for using the entity here, we have to somehow change the domain of our computation, similar to FFT exactly. So our polynomial in the vector for the vector S should be converted to the entity domain, and then we compute the multiplication between them, and the results A times S plus matrix E is defined as a public key at the end of the key generation. And also the entity version of vector S is defined as a secret key.
What does PWM stand for in this context?
Pointwise multiplication.
Okay.
I will actually show you how we calculate the multiplication between these two vectors to each other. Any question about the key generation? Okay, for the encryption and decryption, we have almost the same procedure. The public key goes through, we use actually the message and a random R here as a coin for generating the random value. Again, we choose the matrix R as a random, as we discussed in our previous figures. Let me show you again here, the R. And then we convert it to the entity domain. The multiplication between R and public key as A is computed in pointwise multiplication domain. And we will add the noise and message to it to compute the cybertext and shared secret key. On the other side, Alice again will use the cybertext and her own secret key to regenerate the shared secret key. Okay, let's go through the keygen and see how the polynomial multiplication can be performed. So suppose that you have matrix vector S with only 8 coefficients. It means that degree of the polynomial here is 8. So instead of the regular multiplication between two vectors, which takes an S square, the polynomial over the, ring, the polynomial multiplication over the ring needs an S square, but using this method, you can convert the matrix S to the entity domain. And whenever you have the matrix S in the entity domain, you can easily compute coefficient by coefficient. So S0 with A0, S1 with A1, S2 with A2 in the entity domain, not in the normal domain. Therefore, you have, yes.
Quick question. So is A generated, or I guess created in the entity domain already, or do you have to convert that as well?
Yeah, in the Kyber, we assume the output of the rejection is in the entity domain already.
Okay, excellent, thank you.
That's a good question. So after converting the S into entity domain, instead of performing, for example, S0, A0, S0, A1, we only need to coefficient-wise multiplication to perform coefficient-wise multiplication. So it reduces the complexity of the multiplication here. But we have to pay the cost of the entity conversion, which is not too much compared to regular multiplication. So we use this formula here to convert our vector S to the entity domain, and then the entity of the F can be coefficient-wise multiplied by entity of the G, and the product between them can be converted back to the normal domain using the inverse entity formula here, as shown here. Is it clear for all? I do not go through all details here, but first of all, I would like to make sure the concept is clear.
The notation you have under the bullet polynomial multiplication, like the hollow circle, like that is that implying, or sorry, is that labeling pointwise multiplication between entity F? Okay.
Yeah, this is the pointwise multiplication.
Okay, great.
Any question? Okay, so how we can convert our polynomial to the entity domain? Is it our next actually subject here? We can use the a butterfly architecture, as you see here. Suppose that you have two values, u and v, and then you want to compute u plus omega v mod q and also u minus omega v mod q. This is actually the two inputs of the butterfly, and this is the output of the butterfly. So each butterfly takes two input and compute two outputs. By the way, it has a omega parameter here, which is defined based on the stage of the entity. I will explain it later. So when we have, for example, 8 polynomial of the degree 8, we can categorize it with 4 group of u and v. Each group has 2 inputs and generate 2 outputs. Another thing is, since 8 is equal to power of 3, we have 3 stages of the butterfly computation. So you see that the entity here, entity computation here, has 3 stages: stage 0, stage 1, and stage 2. And inverse entity also has 3 stages. For each stage, we have to categorize our input in 4 groups of 2 and feed it to our CT butterfly. So if I submit here, this is my first butterfly computation. I feed it by S0 and S4, and then I will give the S0 here and S4 here. This is my second group, third group, and sorry. And this is my first group. Is it clear so far? In the stage 1, we categorize our input in 4 different groups. Each group takes 2 input and compute 2 outputs. In the second layer stage, I categorize if it's S0 and it is S4, it's S2, sorry, and this is S6. I categorize them in this way: S0 with S2. So it would be my second category. Is it clear? And S4 with S6. So is it clear, guys? Does it make sense? How we categorize them? S0 with S4 in the first stage, the output is again S0 and S4, S2 and S6 in the second group, S2 and S6 here. Then we choose S0 with S2 and feed it to the second stage of the butterfly. And in the second group, S4 with S6.
It makes sense.
Perfect. So here in the output, again, we will have S, let me write the coefficients, 0 here, 4 here, 2 here, and 6 here. And then I choose S0 with S1. S1 is here. 5, 3, S0 with S1. This is the first group in the third stage. And compute the 2 outputs for this butterfly as well. So again, we have 4 groups of butterfly in this stage of the entity, and we can compute the output of the butterfly here. So you will see that for each stage, you have different omega. Here, omega power of the 0. In the second stage, the power of the omega is increasing by increasing the group. And here again, it's increasing. So using this algorithm and this method, we can calculate the entity of vector S and convert it into the entity domain.
Hey, Moshtaba, I have a quick question.
Yes.
So like if we consider S0 at the very top of the left NTT diagram that you were just showing us.
Mm-hmm.
So even though those numbers get mixed and matched, S0 is still considered that top row all the way from left to right. Is that right? Like, so am I phrasing that correctly?
Could you please again repeat your question?
Sure, yeah. So like if we like the top row that you have labeled S0, right?
Okay.
Yeah. So like that, even though that original value is mixed and matched several times in each stage, we still consider the top output as S0 all the way over. Okay. Okay, gotcha. All right. Okay.
This is the S0 here, but I actually didn't. How we choose and categorize our input in each stage are actually different. In the last stage here, the difference between each we choose, for example, Si with Si plus 1. Okay, actually the distance between the coefficients are defined by this coefficients, by this actual equation. It means that the distance between Si and Sj is 2 power of the n, while the n is equal to the 1 in the last stage, equal 0 to the last stage, 1 for the stage 1 and 2 for the stage 0. Does it make sense?
Yes. Mhm.
Yeah, so we can categorize them in this way. And here the output would be S0, and here the output from here will be multiplied with the A1 and so on. For the inverse entity, we have almost the same butterfly architecture with some minor changes. You will see that the order of the computation is changing, but again, you will have one modular addition, one modular subtraction, and one modular multiplication in different order to compute the output. Again, it takes 2 input and compute 2 outputs, and using again 3 stages, we can convert back our results to the normal domain. Any question? Okay. So if we go through the hardware architecture, there are several techniques that we can increase the speed of the computation. For example, how we can merge the layers of the entity together instead of performing one butterfly computation in each step. We can somehow increase, because you see that they are independent to each other in the same stage. There is no data dependency between the computation in stage, for example, 0. So we can increase the number of butterfly computation in the hardware if we want by parallel computation. And also we can somehow merge the layers together to increase the latency, to increase the speed. But I do not want to go through their details. And yeah, it's actually the Kyber Python code. If we want to go through it, I don't know how much time we have, but yeah. Professor, do you want to go through the code as well, or for now it's enough?
I think if we have another meeting, that would be great. A little bit more details or something. I know you're busy too, but that's good for now that students can play. Please send that GitHub thing that I sent you, the Python thing, that they can start playing with it and they can ask questions. Hopefully you can help us a little bit here. Any other questions, students?
No, but I just want to say thank you so much for the presentation and for your time, Moshtaba. It was excellent.
Thank you.
Yes, thank you so much.
Thank you. Feel free to ask question. If you have any question, please send me an email or ask now. I will try to explain better.
Thanks, Moshtaba. Great presentation, really. Thank you so much. A lot of information.
No problem.
All right, Moshtaba, sounds good. Thank you for your time. I'll get this recording and I can email you guys from the cloud so you can watch later if you want.
So a quick question. So the polynomial multiplication that you're showing here in the code that was on the next slide, is that what we're doing, but we can't see it because it's coding? Or is this more just the theory of something more complicated than the actual code?
It's exactly the code that you have to implement for the Kyber. So you have to implement the entity computation and convert your output from the CBD sampling unit to the entity domain using all this computation. So if you go through the Python code or the reference code for the Kyber, you can see there is a module named entity, and you see that it takes a polynomial of degree 256 and will generate another polynomial of 256, and inside it, you will see all this computation.
Thank you so much.
No problem. Okay, all right.
Sounds good. Let's wrap up. Thank you, Mushtaba, everybody. Okay.
Thank you.
See you next time, everybody.
Yes. Thank you again. Have a great day, everyone. Thanks.
Bye.
Bye-bye. Good.